Hello, everybody. Today we will be talking about in the class Introduction to Robotics. You will be using MATLAB and Forward Kinematics to make a robot move. So, first off, let's take a look at our code here. Uh, if you're watching this video, then I'm assuming you're probably already at least maybe halfway through a semester in your intro to robotics class and you got a project to do. But all right, so essentially the way this is going to work, I had originally made I made my own robot. I'm made some SolidWorks models on SolidWorks, and let's actually just go ahead and take a look at those real quick. Classes, intro to robotics, components. All right, let's open up SolidWorks real quick. So essentially in my project that I had to do, we had to use Forward Kinematics, uh, make a robot be assembled, and then if you can, uh, make it do some movement. That was for part one of our project. Actually, it's just the assembly part really was. But let's take a quick look here. Anytime today. Cool. So if we take a look at this, this is like the base of my robot. The other component is going to be inserted in there and so on. So what you want to do, a good note to know in case like you're trying to do this and you're having issues, go down to tools and options. And let's go to export, file format, STL. So here, if you've already been trying to do this and you're having issues, you may have run into this. Um, so whenever we're going to end up turning this SolidWorks file into an STL file. However, we want this little box checked where it says do not translate STL output data to positive space, because if you have your origin of your part, which is essentially where you would have your frame assigned, if you have a good on SolidWorks, when you export it as a STL, it will shift your part to a corner piece. And then you're wondering why on MATLAB it's not working when it should. All right, so I already saved all my parts. I already exported them as STL files, and I moved them into my MATLAB folder. So to go a little bit through on my code, this is essentially the import. Then I make a little plot to show all my pieces, how they look like whenever they're imported. So next, after that, you want to do some static transformations, which essentially what you're doing with this, these are my actual like operations. Here's me actually using the operations to each specific piece or component. And so the point of the static transformations portion is so your components can be aligned accordingly, like according to your frame that you to your DNH frame that you drew. Um, if you're wondering what this transformation function is, you will need to make a separate file over here or make a separate script. This is more of like a shorthand way of instead of like needing to type all this out individually for each time you're going to use it, you can just label it transformation and then like put in your inputs, um, and it'll simplify your code into making it look a lot prettier. But keep in mind that you do have to have the transformation script in that same folder as to where you're working with all your components. All right, so here I'm applying my RZ transformation matrix into my R3 component. Same thing here. It's my B5 component. Let's take a look at this real quick, and like we'll stop at this portion right here. Let's run it real quick to see what the whole result of my entire code does, and then we'll continue on. So I'm gonna run this section. So all this movement that you're seeing is actually just another iteration calculation. Like each movement step is a separate calculation. I decided to display the iteration and the inputs of my joint variables, which in my case was going to be theta 1, theta 2, theta 3, and my D4 distance. So let's take a quick look at this. Oops, probably should have Control T. Lets you uncomment a whole section. It's a good little shortcut hotkey. All right. So if we're looking at these, my STL file, its frame is actually imported from my SolidWorks part directly into this, and this is how it actually pops up. This is how they are imported. This is how they look. Well, according to my DNH frame, my positive x-axis for my blue component needs to go along it. So I applied my static transformations, and this allowed me to get my blue component according to the way I needed it with the X frame or with the X direction going that way. And moving on along my code, we have our DNH table information. So I essentially, like, I knew what my joint variables were, and like the values I assigned to this was more of according to my drawing of how I had it assembled, because if you have it in a certain fixed orientation, then you're gonna have a certain like angle and position. So I decided to just put mine all completely vertically straight. So here we have for our I1, I2, I3, I4 information. And here we go into my little for loop to get it moving. This is essentially just um, the if statements are telling it like between which iterations, like I'm gonna tell it to do something. So between these iterations, between 90 and wait, if I is less than 90, oh yeah. Um, yeah, so these are my conditions. If my I is, as long as my I is less than 90, it's gonna be doing this. And if it goes from 90 to 135, it's going to do this, so on, etc. This is just my little display portion that you see right here, just to kind of keep up with what it's doing. If you want to just try like a fully assembled view, you don't really need this portion. You can skip down to the actual Forward Kinematics section. Here we have our T matrices solved according to our like little handout It tells you what ti projected into I minus 1, and that's referring to these. I had 4 degrees of freedom, so therefore I only had 4 of these calculations, and then this is my actual T matrices of each frame projected onto the 0 frame, and that's calculated. Well, now let's look at our images. Figure 2, figure 3. If any of y'all just saw my screen down here, this figure 4 is for my second part of my code, which involves the inverse kinematics. We don't need to worry about that right now. All right, so the point of the actual application is once you have your parts in your correct frames assigned, then you should be able to apply these T transformations accordingly to each part. So we're actually going to start off not with the base, but with your second component, which would be my green one right here, is my R2. So R2 is now going to be, its position is going to be transformed from its original statically correct orientation. It's going to be transformed using that transformation matrix into whatever position I need this accordingly. And you do that to each component. So my green, my blue, my black, and my little piston. So that's being applied here, 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 and here. Then figure 3 shows, my bad. Figure 3 shows the resultant orientation. So in a sense, you're just moving each component in space to a specific orientation, and those movements just happen to be, which is the whole purpose of the math being done, happens to be for them to be positioned in a manner that it looks like they all stay connected and moving accordingly. And because of my for loop, all I'm doing is just changing my theta 1, theta 2, or theta 3 inputs accordingly. And the way I did it to show each movement one step at a time, or you can make it all the changes simultaneously. If you're wondering about how did I make it go up and down, you can use the sinusoidal function to create that. And this pretty much clears up your forward kinematics MATLAB portion. So as a recap, we assuming that you make your parts in SolidWorks, their origins are set somewhere. You make sure that when you export them as a STL file, the origins stay where they should be. And if you originally made your parts like according to your DNH frames correct the first time, then you don't really need to do static transformations. I messed up on one of my SolidWorks orientation components, and so therefore I had to apply some static transformations in order to get in the correct orientation for my DNH frame to go accordingly. So now that you have everything oriented correctly, like each origin right where it's supposed to be, then we go on to calculating your transformation matrices, which you're going to apply those changes to your original to your original statically oriented components. And essentially what this is doing is just so you don't get confused on like using the previous one. What it's doing is I'm just going to change theta 1 in this case, for example, is it's taking the positions of all this using theta 1 and then popping out whatever orientation of its assembled version. And then whenever it goes to a new theta 1, let's say from 45 to 90, all it's doing is it's going to take this same original orientation here and then apply the 90 and then pop it out into the assembly. So there may be a case where if you think you're almost there and you're having an issue with the fact that it's blowing up your robot, even though you got it to assemble correctly the first time, what you're probably doing is you're assembling it correctly, but then you're adding transformations to the assembled robot, and then it's exploding your thing. So that's why the whole idea is you're applying the transformation to this setup and then putting it in one orientation and then adding another input. So, and it takes this orientation, then puts it out in a different assembled orientation. So that could be a little troubleshooting guidance for you guys. I think that pretty much narrows it down for that, for anybody that may be having trouble with that. I will be uploading some guidance on inverse kinematics. I didn't get it fully done, but I can provide you with enough help that maybe you can get there a lot easier. But please leave a like, smash that like button, and subscribe if you guys want to keep up with any new content that I may be putting out. And thanks again. We'll see you guys.